Urban resilience at the neighborhood scale is an evolutionary process where the built environment, hardware, and community networks, software, co-evolve. Moving beyond engineering resilience, which seeks a return to a predefined equilibrium, we adopt the evolutionary resilience paradigm. This approach emphasizes modularity, redundancy, and social agency, allowing complex adaptive systems to undergo transformative change in response to chronic stresses and acute shocks. Building on the hardware versus software framework, this presentation explores urban resilience by balancing physical infrastructure with social capital across 6 global case studies. We begin with Barcelona's superblocks, showcasing tactical and evolutionary adaptation, and New York's Hunts Point, which exemplifies systemic resilience in critical food supply chains. The analysis shifts to Copenhagen's street Kields, where blue-green infrastructure, BGI, serves as a social asset, and Concepcion, which highlights the importance of situated knowledge in local planning. Finally, we examine Medellin's success in fostering civic trust through participation in Tokyo's Kyojima district, which maintains resilience at a human scale. These diverse approaches are synthesized into a comparative resilience matrix to identify the structural and social anchors necessary for a sustainable urban future. Urban resilience is built upon 2 essential pillars: hardware and software. Hardware represents the physical environment, including infrastructure and technical upgrades. Software encompasses the social dimension, such as community networks and social capital. The true strength of a city lies in their synergy. While hardware acts as a physical shield, the software is what activates and sustains the system. The Barcelona superblock model is a global benchmark for urban modularity and geometric redundancy. By reconfiguring the CERTA grid into 3x3 block modules, approximately 400 by 400 meters, the city redirects through traffic to the perimeter, reclaiming the interior for social life. The physical transformation involves converting 60% of previous road space into porous, green, citizen squares. This is not merely an aesthetic change but a systemic, hardware upgrade aimed at mitigating the urban heat island effect. By replacing asphalt with permeable surfaces and deciduous trees, the microclimate is regulated, and stormwater management is internalized. Beyond physical metrics, the superblocks function as a social stage. They enhance bonding capital by providing third places that facilitate natural surveillance, eyes on the street, and reduce social isolation, especially among the elderly, a factor critical to reducing heatwave mortality. The use of tactical urbanism, low-cost, temporary interventions like paint and planters, allows the city to test designs in real time. This learning by doing method, supported by parametric traffic modeling, ensures that the displacement of cars does not lead to systemic congestion on primary arterials, effectively balancing local livability with citywide logistics. This strategy reinforces the neighborhood's evolutionary resilience, allowing the urban fabric to adapt its function without destroying its historic form. Hunts Point, a primary food hub for 22 million people, exemplifies passive survivability within industrial residential interfaces. The project emphasizes that resilience must be systemic, ensuring that critical functions persist even when the larger city grid fails. The hardware strategy focuses on a tri-generation microgrid and a combination of static and deployable flood barriers. This microgrid allows the food distribution center to island itself, maintaining essential refrigeration during regional power outages. Furthermore, the inclusion of a maritime emergency supply chain adds a layer of geometric redundancy, ensuring that if road networks are severed, the city's food supply remains intact. This case proves that critical infrastructure must be socially embedded to be truly resilient. Socially, the project is rooted in the Hunts Point Lifelines coalition, which builds bridging capital between industrial stakeholders and the low-income local community. This ensures that technical robustness translates into local economic security and prevents post-disaster gentrification. The methodology derived from the Rebuild by Design competition framework, which used vulnerability mapping to identify not just infrastructure at risk, but also the socio-economic vulnerabilities of the workers. This climate neighborhood demonstrates how to treat climate adaptation as a multifunctional urban resource through the strategic implementation of nature-based solutions, (NBS). By integrating flood management with public space, Copenhagen has shifted the urban resilience paradigm from hidden engineering to visible social infrastructure. The physical strategy centers on the concepts of cloudburst streets and sponge plazas, exemplified by Tessinge plaids, which act as a distributed network to sequester and channel rainwater, thereby preventing catastrophic sewage overflow during extreme precipitation events. A critical technical component of this hardware is the use of topological hydraulic modeling. This tool allows planners to utilize the city's natural topography to redirect floodwaters toward the harbor using gravity alone, significantly minimizing the reliance on energy-intensive mechanical pumping systems. The social software of the project is rooted in citizen science, where residents are not merely passive beneficiaries but active participants in monitoring environmental data through digital applications. This high level of engagement fosters an intense sense of place attachment and communal stewardship. Unlike traditional, gray infrastructure, which is typically subterranean, purely technical, and invisible to the public, Copenhagen's BGI is designed as a third place. By allowing residents to co-design the specific types of vegetation and the spatial layout of the plazas, the city has ensured that these flood management zones provide high-quality recreation 365 days a year. This transformation of infrastructure into a culturally valued asset creates a social buffer. A community that maintains its parks and monitors its local environment together is mathematically and sociologically more likely to activate effective mutual aid networks and collective response mechanisms during a catastrophic flood. Consequently, St. Kjeld's proves that adaptive resilience is most successful when the technical hardware is used as a vehicle to strengthen the neighborhood's social software. Following the 2010 8.8 magnitude earthquake and subsequent tsunami, Concepcion shifted from traditional, top-down reconstruction to a sophisticated model of transformational governance. This case highlights the transition from engineering resilience, simply rebuilding what was lost, to evolutionary resilience, where the disaster serves as a catalyst for systemic urban improvement. The physical hardware strategy focuses on dissipative infrastructure, designed to absorb and diffuse the energy of natural forces rather than rigidly resisting them. A cornerstone of this approach is the creation of coastal forest buffers, tsunami mitigation parks, and the deployment of modular housing units equipped with seismic isolation technologies. These physical barriers are strategically integrated into the urban fabric to act as first responders during seismic events. However, the system's core strength lies in its social software, specifically the institutionalization of neighborhood reconstruction committees, mesas territoriales. These committees utilize situated knowledge to identify micro-vulnerabilities that centralized satellite maps and high-level bureaucratic planning often overlook. For example, local residents identified hidden bottlenecks in escape routes and high-risk zones for elderly populations that were invisible to external architects. Through collaborative scenario planning, residents and planners co-created evacuation protocols that are physically grounded in the new urban layout. This approach turned what could have been a one-time reconstruction effort into a permanent adaptive management system. By designing the coastal barrier as a multifunctional public park, the city ensured that the infrastructure remains an equitable social asset, used daily for recreation rather than existing as a derelict, disaster-only zone. The integration of these layers prevents the decay of resilience over time. Because the community is perpetually engaged in the upkeep and recreational use of their protective measures, they maintain a high state of disaster memory and readiness. This socio-technical synergy moves the neighborhood from mere resistance to evolutionary adaptation, where the urban morphology itself facilitates a continuous state of preparedness and social equity. Medellin's integrated urban projects represent a transformative shift in global urbanism, demonstrating how morphology and high-quality architecture can serve as primary tools for social repair in fractured, high-conflict communities. The Medellin miracle is characterized by the philosophy that the most beautiful buildings must be in the most humble neighborhoods, utilizing urban design to restore state legitimacy, civic dignity, and long-term evolutionary resilience. The physical strategy centered on infrastructural integration to overcome the extreme topographical barriers that historically isolated the hillside slums from the city's economic and social valley. The implementation of the metro cable system served as a profound mobility innovation at the urban margins. This system did more than provide efficient transport. It established a vital link between morphological connectivity and the democratization of urban resources. By physically bridging the gap between the periphery and the core, the state effectively integrated marginalized citizens into the formal urban fabric, transforming their daily experience from one of isolation to one of belonging. The innovation of the Medellin model, however, reaches its peak in the creation of library parks, e.g., España Library, San Javier Library, which act as socio-technical anchors. These structures transcend their architectural form. They are high-quality platforms for education, social services, and political participation. Through strategic urbanism, these landmarks were placed in forgotten zones to signal a shift from state neglect to radical investment. The success of these anchors was not accidental but dependent on an intensive co-design process. This participatory methodology acted as a primary driver of civic trust, confianza ciudadana. By involving residents in the planning and definition of these public stages, the city moved beyond top-down provision toward a model of collective stewardship. Utilizing community mapping to determine anchor placement where social ties were weakest ensured that these projects functioned as neutral spaces for social reintegration. The result of this synergy, combining the morphological connectivity of metrocibles with the participatory software of the library parks, was a dramatic decrease in homicide rates and a quantifiable increase in communal adaptive capacity. This case proves that physical hardware is most effective when it is designed specifically to rebuild the social trust and political legitimacy of a community, turning urban design into a vehicle for social justice. Kyojima serves as a preeminent global study in maintaining fine-grained texture while simultaneously increasing fire safety in high-density wooden residential areas, historically known as Mokachin districts. Unlike the scrape and build approach typical of post-war modernist planning, Kyojima demonstrates that resilience can be surgically embedded into an existing traditional urban fabric. The physical, hardware, strategy is defined by micro-scale interventions, where the city eschews mass demolition in favor of strategic, firebreak, pockets and selective street widening at critical intersections. This ensures that the neighborhood can withstand acute shocks, specifically the rapid spread of fire following a major seismic event, without causing the social displacement often associated with Western-style urban renewal. A key financial and structural tool is the fireproofing subsidy, which incentivizes residents to rebuild individual houses with non-combustible materials while strictly maintaining original small-scale lot boundaries. This preserves the dense, walkable morphology that defines the district's identity. The social software of Kyojima is rooted in the philosophy of Machizukuri, community-led town-making. In this paradigm, the neighborhood's intense social networks are treated as a living infrastructure, functioning as human sensor arrays and immediate first responders. The resilience is institutionalized through participatory GIS mapping, where residents themselves identify micro-vulnerabilities, such as narrow alleys blocked by private flower pots or non-functional hydrants, which centralized authorities might overlook. Furthermore, the community is trained in autonomous disaster response, utilizing resilience kiosks, disaster storage sheds, strategically placed throughout the neighborhood. By keeping the urban fabric at a human scale, Tokyo preserves the high social proximity required for rapid, door-to-door response. This case underscores that resilience is not merely a structural achievement but an incremental adaptation process. Here, the community's social fabric is preserved as the primary driver of survival during the golden hour, the first critical hour after a disaster when professional emergency services are often overwhelmed. Kyojima proves that a soft network of informed, connected citizens is the most effective backup for hard infrastructure in high-density environments. The comparative resilience matrix serves as a strategic framework to evaluate how diverse urban environments synthesize physical interventions, hardware, with communal dynamics, software, to achieve systemic longevity. By categorizing resilience into specific paradigms, evolutionary, engineering, adaptive, transformational, social, and incremental, the matrix illustrates that there is no one-size-fits-all solution. Rather, resilience is a context-dependent evolutionary process. In the cases of Barcelona and Tokyo, the matrix highlights the critical role of urban modularity. In Barcelona's evolutionary paradigm, the hardware is not just a road closure but a reconfiguration of the CERTA grid into 3x3 modules. This creates geometric redundancy, ensuring that while the perimeter handles city-wide logistics, the interior serves as a social buffer. Similarly, Tokyo's incremental approach focuses on the fine-grained texture of the Kyojima district. Here, the hardware consists of micro-scale firebreak pockets. The matrix reveals a key lesson. By maintaining small-scale lot boundaries and social proximity, Tokyo preserves the software of Machizukuri networks, where residents act as human sensor arrays, proving that modularity prevents cascading systemic failures. The engineering and social paradigms, represented by New York, Hunts Point, and Medellin, emphasize the concept of the socio-technical anchor. In New York, the focus is on passive survivability, the ability of a neighborhood to maintain critical functions during a total grid collapse. The hardware, tri-generation microgrids, is anchored by the software of bridging social capital, ensuring that industrial resilience translates into local economic security. In contrast, Medellin uses high-quality architectural anchors, library parks, to repair a fractured social fabric. This social urbanism demonstrates that physical connectivity, metrosymbols, is most effective when it is utilized as a vehicle for radical inclusion, transforming the neighborhood from a zone of violence into a cohesive social organism. The matrix further explores the relationship between climate adaptation and political agency through Copenhagen and Concepcion. Copenhagen's adaptive paradigm utilizes blue-green infrastructure to treat rainwater as a social resource. The hardware of sponge plazas succeeds only because it is supported by the software of citizen science and public trust. When residents monitor environmental data, they develop place attachment, turning technical drainage into a communal asset. On the other hand, Concepcion's transformational paradigm focuses on dissipative infrastructure. Following the 2010 earthquake, the city moved beyond mere physical reconstruction to institutionalize neighborhood reconstruction committees. The matrix shows that by integrating situated knowledge, the micro-details of evacuation routes known only to locals, into formal risk governance, the city achieves a level of disaster preparedness that top-down engineering cannot match. In conclusion, the matrix demonstrates a fundamental law of urban survival. Hardware provides the shield, but software activates the system. Whether through the tactical urbanism of Barcelona or the micro-interventions of Tokyo, the most resilient neighborhoods are those where technical assets are treated as communal platforms. By balancing morphological redundancy with social capital, these cities move beyond simple resistance and toward an evolutionary resilience that allows them to learn, adapt, and thrive in the face of uncertainty. The comparative analysis of the 6 global case studies, Barcelona, New York, Copenhagen, Concepcion, Medellin, and Tokyo, provides a definitive roadmap for the future of urban planning. The integration of these cases confirms that the most resilient neighborhoods are not those with the highest walls or the most expensive technology, but those where hardware is modular, redundant, and passive, and software is inclusive, participatory, and data-driven. Resilience is not a final destination or a static metric of resistance. Rather, it is an evolutionary state achieved when technical assets, be they flood parks, microgrids, or libraries, are treated as communal platforms. The following key takeaways summarize the essential strategies for fostering this socio-physical synergy. The principle of socio-technical integration. Technical infrastructure must transcend its primary engineering function to serve as a social asset. In Copenhagen and Barcelona, drainage systems and traffic grids were redesigned to function as third places, recreational zones that facilitate daily human interaction. Takeaway. When resilient hardware is visible and socially integrated, it fosters place attachment. This emotional bond ensures that residents treat infrastructure as a communal responsibility, increasing the likelihood of stewardship and rapid activation during a crisis. 2. Morphological redundancy and modularity. The cases of Barcelona and Tokyo illustrate that the physical layout of a neighborhood determines its survival capacity. By breaking the urban fabric into self-sufficient, modular cells, cities can prevent cascading failures. Takeaway. Morphological redundancy, whether through 3x3 grid modules or fine-grained firebreaks, ensures that if one system component fails, the neighborhood remains functional as a whole. Modularity allows for localized islanding, which is the cornerstone of systemic survivability. 3. Passive survivability through distributed systems. The New York Hunts Point case emphasizes that critical infrastructure must be designed for autonomy. High-tech hardware, like tri-generation microgrids, provides the capability for passive survivability, allowing essential services, like refrigeration or lighting, to persist even when the centralized city grid collapses. Takeaway. Centralized systems are inherently brittle. Future resilient neighborhoods must prioritize decentralized, distributed energy and water networks that can function independently during a disaster. IV. Transformational governance and situated knowledge. The most effective resilience software is built through the institutionalization of local participation. As seen in Concepcion and Medellin, top-down planning often misses micro-vulnerabilities that only residents can identify. Takeaway. Utilizing situated knowledge and citizen science shifts the role of the resident from a passive victim to an active agent of survival. By empowering neighborhood committees and using participatory GIS tools, planners can create high-resolution response strategies that are socially equitable and physically grounded. Versus incremental adaptation versus radical renewal. Tokyo's Kyojima district teaches us that resilience can be achieved through incremental adaptation rather than wholesale demolition. Preserving the fine-grained texture of a neighborhood maintains the social proximity required for mutual aid. Takeaway. Resilience strategies should aim to upgrade the hardware, e.g., fireproofing, without destroying the software, e.g., long-standing social networks. Small-scale, continuous improvements often produce more robust social outcomes than large-scale, disruptive urban renewal. In conclusion, the synthesis of these global models demonstrates that hardware provides the physical shield, but software activates the system. Transforming a static built environment into a dynamic, adaptive organism requires a paradigm shift. We must stop designing neighborhoods as rigid machines and start nurturing them as socio-technical ecosystems. The synergy between robust physical morphology and high social capital creates a buffer capacity that allows communities not just to bounce back, but to bounce forward into a more equitable and adaptive future.